Good, hello, good morning. So, 3 more sessions to go, and the topic for the remainder of the winter term is the random field theory based approach to p-value evaluation. So basically the way that the p-values that you see in these tables in software for the analysis of fMRI, but also EEG data, how they come about, and of course also you see these p-values in publications a lot. And so this kind of topic has various names. Some just call it or want to call it random field theory, so RFT. Other people call it topological inference, which also makes some sense because it's about inference on topological features of random fields. And I think a good name is random field theory based p-value evaluation, because that's what happens. But not all of my reviewers, actually none of my reviewers, agree that RFP is a good name. Anyway, so that's the name. And what this whole thing is of course based on, and the background is, at least to a certain degree, the idea of multiple testing, control, and what we've learned there about the multiple testing family-wise error rate control, and what we learned about the maximum statistic in this regard, by maximum statistic. So this of course rests on these the stuff that we've discussed over the last 4 sessions, or 4 hours or so, by maximum statistic. However, it also does a little bit more in the sense that it establishes a spatial model for fMRI. So as you will remember, so far we discussed everything in this mass univariate framework, where we essentially considered one voxel. And then we said, well, we do this for many voxels. So we had the time series of fMRI data for one voxel V, and we modeled this by a design matrix, some voxel-specific beta parameters, and some voxel-specific error. And V then was, so the same kind of model, and especially the same design matrix, was used and is still used also in what we're doing now for all voxels. But this basically, of course, completely neglects the idea that if you have voxels, for example, if you look at 2D, that there are spatial relationships between the voxels. So, for example, this voxel here is closer to this voxel and is further away from this voxel. Don't know why I put a 5 there. Yeah, but the way we are analyzing the data right now in this GLM base, in the mass univariate GLM way, is we analyze this, and then we get a t-value for this one. We analyze this, get a t-value for this one for a given contrast, of course. We analyze this, get a t-value, and then we analyze this. So we're basically treating the data, if you want, and without any technical meaning associated with it, as spatially independent data sets. We just don't care where they are located in space. Now at the level of inference, maybe I should do it with the t-values, actually that's more instructive. At the level of inference, the standard way to analyze fMRI data actually accounts for the fact that there is a spatial arrangement. So let's do this again. So here we have a t-value of voxel 1, here of voxel 2, 3, and so on. So we have many t-values after we ran a GLM analysis for each voxel. yeah? And so on. And now, of course, we can, and this is also happening, namely at the uncorrected level, we can just compare each of these t-values to the t distribution for the appropriate degrees of freedom. So, for example, if this is the t distribution for, let's say this is a t-value that is formed by analyzing beta parameter contrasts over, let's say, 40 subjects, then we have 39 degrees of freedom t distribution. We have observed a specific t-value and, for example, here t5, and we can then, under the assumption that this contrast of beta parameters has a distribution centered at 0, we can evaluate the probability to observe a larger, a t-value larger than the observed one. So the probability for the t statistic to exceed this value 5, and that's then our uncorrected p-value. Yeah, so this is just doing one sample t-tests at each location where we evaluate a t-statistic. Yeah? Questions about this, because if you don't understand this, then you're doomed. Is that clear? So we just do one sample t-test over contrast parameter estimates, in this case for a number of subjects. You always have to think that we can do this inference in at least two scenarios. One is that we have data from one subject and we do a t-test by considering the inter-subject variance, so do the t-statistic based on a single subject's data, or we take these contrast parameter estimates from a number of subjects to the second level, as it says, and then we have a data set that corresponds to the contrast, which are just single numbers over n subjects, and then we do a one sample t-test design over that. Yeah? So these are the two scenarios. The latter is called group analysis. The first thing is called single subject analysis. There are more options, so that's not the only thing that one can do. But in both scenarios, we would apply then the random field theory based p-value evaluation. Yeah? Good. So what then random field theory brings to the table is a number of things, actually. The first thing is that we go from a voxel null model, if you want, which is the single t distribution, from a voxel null model to a let's call it brain null model. So although it's more like a 3D null model. Yeah? And that's maybe even the most important thing about the random field theory based approach. So right now we model the distribution of a single t statistic under the assumption that the null hypothesis holds, so that there is no effect. The most basic thing in random field theory based approach is to, instead of considering a single spatial location, to consider all locations in 3D. But because 3D is a little bit hard to draw, we will, so when I now introduce this, I will draw it in 1D. In the script you see visualizations for 2D, so where you then have surfaces. In 3D you have to think about the whole thing, it's basically then creating kind of a blob structure in 3D. So what do I mean by this brain null model? So let's say we have a one-dimensional space now. So we have this, and this is space. So right now, what we have is, of course, we have our voxels, which are at discrete locations in space. And for each of these voxels, we consider a t-distribution. So if you want, you can, although it's pretty meaningless, but you can draw something like this over each voxel. Yeah. So this is just this. It's not really something that makes a lot of sense from an informal way to formal way to draw something like this, but just to give you an idea. But right now we have the null model here, which is the t-distribution here, which is the t-distribution here, which is the t-distribution, and so on. Now the first crucial thing that random field theory brings to the table is a spatial null model that talks about the distribution of the statistics of interest over space. And this is then usually, or this kind of null model, so a model that describes how the statistics are distributed when the null hypothesis is true, is called a random field or random process. Random field. In this case, if the space is actually one-dimensional, or if you have a one-dimensional parameter, it's called random process. So you might have heard of Gaussian processes. These are Gaussian, so when we later talk about Gaussian random fields, if the space parameter is one-dimensional, these are called Gaussian processes. So the first thing important about random fields is that instead of allocating random variables at these discrete locations, they allocate random variables over or basically everywhere in space, so to each real number. Yeah? So instead of having only a random variable at the location of the voxel, which we have there, we now have a random variable everywhere in space. The other thing is that the random such a random field comes with a parameterization of its behavior in terms of the covariation of all random variables that are there. And the main point that we will make is that the random field can have a given degree of smoothness. Now, what happens? So the first thing that you should appreciate is that if we have a random field, we have infinitely many random variables over space. If we draw a sample from this random field, we get not like here. So if we draw a sample from this t-distribution, we get a t-value here. Yeah? Or if we do another realization, we get another t-value here or another t-value here for a third realization. Now, if we draw a realization from a random field, we get a value for each of the random variables. And because each of the random variables, because they're infinitely many, it essentially corresponds to a function over the real numbers, so over space. So if I draw a realization from a random field, I would get something like this. Yeah. If I draw another realization from the random field with similar properties, I could get something like this. And let's draw another realization. If it is again a random field with similar properties, I would get something like this. Yeah. So these are random field, in this case actually random process, because we're looking at one-dimensional random fields, so where the parameter is one-dimensional realizations. Now, what about these realizations? One thing that is quite important is that we assume that the expected value of each of the random variables that constitute the random field is 0. Because we want to create a null model. Yeah? So the expectation, so if we would draw more and more of these realizations and average, And then basically by the law of large number approximate the expectation at each location by the average. The expectation would be 0. So the expectation of our random field here, which we will of course formalize, is 0. This means that you can now create these kind of random field realizations, but they don't model any activation somewhere. They just model on average 0 activation, but depending on their smoothness, sometimes a little bit of a something larger than 0, sometimes a little bit smaller than 0, with some spatial correlation. Yeah, so you can basically, if you want, consider this the t value axis, and now create realizations of these random fields under null model. Yeah, so we don't have to. Of course, random fields are not restricted to be used as null models. We could, of course, also have some deterministic variation over space, and then add to it a random field, so that we have, like the GLM, some deterministic excursions over space plus some noise. But here we are just realizing null model random fields. Yeah. Questions about this so far? Good. And this is maybe already the most important thing about the random field stuff, because what we will do, everything that we will do is based on this kind of setup. Because what we will be interested in is to compute the probabilities of the certain features of these random fields under this null hypothesis, and compare that with our data. So let's continue a little bit. So these would be random field realizations. And space is, of course, representing the brain. Yeah. Now, the random field that we are interested in are mostly actually T random fields, so random fields with T variables at each location. They can have different properties. One thing that's always the case is that they have expectation 0, because we want to model null distributions. However, they can have different levels of smoothness, and this will be one important thing. So something that is very smooth, has high smoothness, that's for example smooth. It's very smooth. And something that is less smooth has lower smoothness. Yeah, so that's low smoothness. It's rougher. And why this is important is because the probability for features of these random fields, for example, in this case, this will not be important, but just because it's very easy to see here. As you see here, the blue crosses the, could actually be any, but the blue crosses the 0 many times, whereas the pinkish crosses the 0 only twice. So the probability for 0 crossings for this low smoothness and high smoothness random fields, and in this case random field realizations, the probability for 0 crossings is different. Yeah? So the probability of this feature, which will not be an important feature, but others will be, depends on the degree of smoothness. Yeah? What happens in fMRI is that the smoothness of the random field is actually based on the data. So the if you have acquired data, then to tune the null model for random field theory-based p-value evaluation to your data set, the smoothness, so the spatial smoothness, is estimated from the data by essentially looking how much it varies over space. That's essentially it. And based on the smoothness estimate, the distributions for the features that we would be interested in, which I will tell you about in a second, differ. Yeah. The other thing, we will get to that. So the other thing is that it also depends how big the random field is. So if you have a very large random field, then you're more likely to have a big value at random than if you have a small random field, because there's just the chances higher that at one point it will actually go over some threshold. But let's postpone that. The problem is, or what I'm pointing here at is that in fMRI you have this notion of results, which combine the notion of volume in 3D and smoothness. So the smoothness story is a little bit more complex than this, but not much, and the intuition is this. So that's random fields and smoothness. Now the question is what kind of features of random fields we're actually interested in. And yeah, so that's the next thing. Or questions about the smoothness thing? No. So now we talk about the random field features for different levels of inference. So we again assume that we have a random field of a given smoothness. We can draw a realization from this, so let's do that. That was kind of the worst realizations for what I want to present. So let's do a better one. So now the features that we are interested in are the following. First, we are interested in the distribution at each location. So we again assume that we have sampled this random field realization at discrete locations, which are our voxels. So these black dots are voxels. And what we want to know, the first thing that we want to know, which is called uncorrected voxel level inference, is something that we've already seen. Or peak inference, it's also called. That's just the distribution of the random field at each location, and this we've already seen. So that was already the point here, that each of these, each of the random variables in a random field has, for example, a t distribution if we have a t random field. If we have a f random field, then each of the individual random variables has an f distribution. Same for chi-square and z random fields. So if we consider only this, then we do uncorrected voxel inference. So this is what you find in the SBM table in the rightmost column, and is just standard T inference. But it's one of the features that we are interested in. The next feature that we are interested in for what is called family-wise error rate corrected voxel or peak inference is the maximum statistic of the random field. So let's our random field, let's call that x, and it is depending on space, so let's also call that x. We will introduce that more formally. And let's assume we evaluate the maximum of this random field. Of course, there is a maximum here, and the maximum is here. So that's the maximum location, and the maximum is itself here. And so if we have the maximum statistic, so if we talk about the maximum statistic, what we of course talk about is the distribution of the maximum statistics. So the probability for the maximum of this random field to exceed a certain value. Let's, for example, call that U. Now, based on what we did in statistical testing in the last weeks, we know that if we have the distribution of the maximum statistic over a set of test statistics, where here actually the set of test statistics is infinite, and we mainly looked at the finite case. It's infinite in the random field, and at discrete level it's not infinite. This is actually one of the unsolved problems of random field theory, I think, how to appropriately express that. In any case, whether it's finite or infinite, if we have the distribution of the maximum and we can solve for this threshold here, then we can establish family-wise error rate control at this at a given significance level. Yeah. So this is what we discussed last week in detail why this works. However, to actually use that, we need the distribution of the maximum statistics. So what we need is some parametric form of the maximum statistics, so that we can ask what is the probability of the maximum to exceed a certain value u, for example a value u that we have observed. So let's say for one voxel we observed a t value of 10, then we can ask what is the probability that the maximum of the random field exceeds a value of 10. And if this probability is smaller than 0.05, for example, then we can say, okay, we declare this significant, and we, if we only use these kind of things as really positive test results, then we have controlled our family-wise error rate over the number of tests that we are doing here, and that's at least the number of voxels. Yeah, so we need the maximum statistic, and the maximum statistic leads then to family-wise error rate corrected voxel or peak inference. Questions about this? So that's not the rightmost column in the SPM table, but the column 1 to the left. So this is essentially what we're trying to do here, and this is also how this whole thing started in the early 90s, is we do many tests over voxels. We need a maximum statistic over voxels. What we use is we use the maximum statistic of the random field that is sampled at the voxels, and by studying this probability distribution of the maximum statistic and then using it appropriately in a significance test, we can establish, or we can do family-wise error corrected inference. However, this is not the only thing in random field based p-value evaluation. It's actually also not the most used one. The most used one is a cluster size statistic, and that's quite different. So maybe we do a new plot. Let's run für 1 voxel inference or peak inference. So essentially, this uncorrected voxel level inference, nobody takes that seriously. So if you have some uncorrected voxel results, that's interesting, you can look at it, but you will, if you try to publish that, and as an important result, people will say, that's uncorrected voxel inference, this is not very significant. So you should correct for the number of tests. If you publish family-wise corrected voxel peak inference, this will be respected. The thing is that you are then very specific in your anatomical location. You say at this voxel, this is significant. The problem is you will often not find significant voxels, or you will not often have family-wise error rate corrected significant results. Hence, what people like much more, because it's often more significant, is random field features 2, cluster size inference. And that works as follows. So again, we assume that we have a realization of our random field. Might even look fairly similar to what we've seen above. And we are now interested in the cluster size statistic based on a given cluster forming threshold. So what now we need is a cluster forming or cluster defining threshold. Which we can choose, and for example we choose it here. So basically, if you want, you can think we mask out everything that is below this cluster forming threshold and end up with these 3 clusters here. Yeah. Now, each of these clusters has a given volume, and this volume, I think we call K. So that's cluster volume K, and of course we have here K1, K2, K3. And what we can ask is, what is the probability for the cluster volume at a given cluster forming threshold to be larger or equal to some value K? And then again, we can take our threshold here such that the probability is lower or equal to alpha, or we can just evaluate. I mean, this is of course always what you can do. You can also just, of course, evaluate what is the probability for the cluster volume at a given cluster forming threshold to be larger than some value K, so for example K1. And if this probability to be larger than, for example here, I don't know, 10 voxels, let's say, is large, then this is not very surprising. If it's low, then it's surprising. Yeah. So let's say the volume here, it's a little bit hard to tell, but the volume here is let's say 8. The volume here is definitely smaller, that's 4, and let's make this a little bit bigger, so that's the biggest one. The volume here is 15. Then the probability for the cluster extent statistic under the null hypothesis, of course always, to be larger than K3 is likely smaller than the probability of the cluster extent to be larger than K1, for example. And the crucial thing here, of course, is that, again, the distribution of this cluster's extent or cluster volume statistic K, U, because it depends on a cluster form threshold, depends on the properties of the random field theory null model. Yeah? So if we have a very spiky, so something like this, then a very spiky random field, then of course the probability for small clusters is larger. If we have something very smooth, then the probability for clusters at a higher threshold either goes to 0, or if it actually crosses the threshold, then it's also going to stay above that for some time, so the probability for large clusters gets a little bit larger. The exact details of this we will have a look at later. But that's the cluster extent threshold. Questions about this cluster extent threshold? Or cluster size or cluster volume, it's all the same. I use these terms because you see all of them in the literature. I use them somewhat interchangeably, which is of course a little bit annoying, but they are there. So this, what I just described by talking about the probability of the observed cluster sizes under the null hypothesis, this is what would be referred to as uncorrected cluster inference. Actually, it should be cluster size inference, because you can, because for example, what you're not completely not talk about is the values. You just talk about the size. You just talk about how many voxels are in the cluster, but you don't talk about at all what the values of the statistic in these clusters are.
Yeah, that would be my question, because you now mark the volume as an integral, or is it only the how many voxels there are? So, or is the volume really the integral?
That's a good point. Yeah, no, you're right. Yeah, sorry. Yeah, here, you're completely right. I confused myself. So it's actually, you're completely right, it's this bit. Which of course in 3D, and this is why I confused myself there, in 3D it's, you can think about the cluster over like a blob in 3D, and then it's actually the voxels are in the blob. But here the voxels and the cluster size is the extent on the x-axis. Yeah, very good. Sorry.
I have another question. Yeah. Because now you said you're forming the clusters with introducing a threshold. Could you also do this with other techniques, like in the deep learning techniques? I think we learned something how to form clusters, like not just put a threshold, but because there are some clustering techniques.
First of all, where did you learn something about deep learning?
Huh?
Where did you, and this is not deep learning, you mean cluster, you mean K means clustering and things like that.
Well, I learned it in my deep learning class last semester.
But that was K means clustering, you mean?
I'm not sure about the right technique at the moment, but
so you mean
also did this, but
so you have something like this, and then you say, okay, this is one cluster and this is one cluster. Yeah, no, that has nothing to do with that. Or let's say, yeah, it doesn't really have to do anything with it, because the way that clusters are evaluated here is based on a connectivity scheme. So the question is, if you have a given voxel and it's above the the cluster forming threshold, then you call this voxel is part of a cluster by looking at the neighboring voxels. So you look at this one, you look at this one, you look at this one. So you have either, what is it? 1, 2, 3, 4, 5, 6, and then you look at the next ones and at the next ones, and you form the clusters by this. So that's the algorithm behind that.
But here you have like everywhere the same threshold, but it could be that like wouldn't it be also good like to vary the thresholds depending on the signal in a certain region?
That's not how it's done. So the threshold is completely uniform, and the thing is that you basically specify the threshold, and by specifying the threshold, the probability for certain cluster sizes under the null hypothesis changes. So the threshold is everywhere the same.
Okay.
Yeah. And cluster. So don't confuse this with k-means clustering or EM-based Gaussian mixture models and so on. This is really has nothing to do with that. If you want to have something to do with it, then that would be a PhD project to study similarities and differences and maybe things that you can take from one to the other. But it's very different. Because here it's really just a geometric a geometric property. Yeah, but thanks for pointing out that the voxels are here and not there. So that's the cluster size statistic in the uncorrected setting. And the final thing that we will have a look at is the corrected cluster level inference. And that's again based, and that's of course family-wise error rate corrected. And for this, we need again the distribution of the maximum cluster extent. So the distribution that we need to develop to be able to do family-wise error-corrected inference at the cluster level is the distribution of the maximum cluster extent, for a given cluster-defining threshold under the null model of the random field. And this was introduced by the mid-90s. And survives in SPM and FSL to this day. And this is also the most used corrected inference statistic. So people usually will report corrected p-values at the cluster level. The thing why this is often more significant or easier to get significant is that the maximum is here formed over, of course, fewer tests than for voxels. So here the family of tests is the number of clusters, whereas here the family of tests is the number of voxels. So because there are fewer clusters than there are voxels, the multiple testing problem is not that strong or not that large, and then to find something significant there is not that hard, because you don't have to control essentially. If you think if you think in a Bonferroni way, you don't have to correct for 1,000 tests, but only for 10, let's say. So this is why usually it's easier to get something significant at the cluster level for the cluster size statistic, which has also been I don't know whether you followed that, but there's been some debate on the validity of this cluster size statistic recently, which however was unfounded. What they showed, so what we will later see is that that all of these probability distributions, so this probability distribution, the probability distribution of the cluster extent, and these distributions of the maximum peak statistic and so on, they are based on approximations, and these approximations hold in the limit of high either maxima or high cluster forming thresholds, but they don't hold at low cluster forming thresholds. And if you use a low cluster forming threshold, then these approximations don't hold, and your inference becomes wrong. But if you use them only in the scenario of high cluster forming thresholds, then they work. And this is also what's been in the recent literature. So if you follow a little bit the Eklund stuff, Friston stuff, and so on, then you see that they initially claimed that everything is probably wrong, but if you look into the paper, you see that it's actually working, but it does go wrong if the cluster forming threshold is not high enough to for the approximations to hold. But this was known before, so it's not that surprising. Good. I think this is kind of the overview, and then I think we can start with actually introducing random fields in the next hour. So are there any questions right now? Yep.
Here, when we are talking about the smoothness, are we talking about the smoothness of data or the kernel, Gaussian distribution kernel?
So you're pointing, so you have apparently read something, which, whatever you read. So we are talking about the smoothness of the random field. The way it's parameterized in brain imaging is by considering the width of a Gaussian smoothing kernel that is applied to a wide noise field. But that's essentially, so what this is a parameterization that this is horrible, but it survives in brain imaging. So this thing here and this thing here roughly has the same smoothness. This would be our random field that we are interested in, and this we can conceive as being generated from a white noise. What that is, we have to discuss, which is smoothed by a Gaussian kernel. And the way that the smoothness in brain imaging is expressed for this random field is in terms of the full width half maximum of this Gaussian kernel. It's quite horrible because it also assumes brings in an isotropy assumption, but yeah, we will come to that. Yeah? But because we usually don't have to assume that this is generated from a white noise process and smoothed by a Gaussian kernel, but we assume this is just the null model for the data. Yeah? Good, then let's have a break and start 5 minutes after 9 again.